Roger and Sasha had asked me to talk a little bit about what are some of the emerging opportunities to study plasmas under extreme conditions in the laboratory, where connection can be drawn between some of these extreme processes with what is going on in astrophysical environments. So I want to get one thing straight from the get-go. The motivation and what I'll be discussing here is not to try to do some kind of miniature analog of a black hole or of a neutron star in the lab. That's certainly not going to happen. It's very clear that the conditions that you find in these extreme cosmic laboratories far exceed what it can produce in the most extreme laboratory experiments. The motivation is instead to realize that with advances in light sources and accelerator facilities, we can now produce in the laboratory conditions in terms of pressure, temperature, radiation, where we can study basic plasma processes in these environments that were not possible to do in a controlled way many years ago. And so the hope is that by producing these plasma conditions in a controlled environment, we can benchmark codes, we can develop better confidence in the models that we are putting forward to describe these basic plasma processes in these extreme conditions. And hopefully there can be some fruitful also exchange of ideas between what is going on to understand observations and what is going on to understand and drive these experiments. All right, so many people have contributed to what I'll be discussing here, both on the theory and simulation, but also experimental side that I want to acknowledge in first place. The idea will be to kind of remind everyone, even though we've been hearing about this a lot in these 2 days, about what are some of the exciting discoveries and the open questions related to basic plasma processes that are associated with them. And the need to understand how these basic plasma processes work in these extreme conditions. I'll then be spending most of the time telling you about new experimental windows that are being opened based both on advances in high-power lasers, but also particle accelerators, which are enabling unique laboratory studies of basic plasma and strong field processes. And we will go from magnetic field amplification and particle acceleration in collisionless shocks to the production of relativistic pair plasmas and the study of QED plasmas, by which I mean plasmas where the interplay and the coupling between strong field QED processes and the plasma collective processes becomes important in determining the dynamics of these systems. All right, so we have already heard in these 2 days quite a bit how important our central plasma processes are to numerous scientific open questions that are raised by these exciting observations in the last decades. We heard, for example, Naomi discussing yesterday about the mechanisms and the possible origin of the highest energy cosmic rays. So how do plasma processes, in particular shocks, as she was describing yesterday, shape the acceleration of these particles all the way to more than 10 to the 20 electron volt? What controls the electromagnetic signatures associated with these compact objects and their mergers? So how do plasma processes and strong field processes dictate the electromagnetic signatures of these environments? Are there new emergent phenomena arising from the interplay between strong field QED effects, for example, and plasma collective processes? And I would add here, can we study and harness these processes to produce more efficient accelerators and light sources, for example, in the lab? Can we also be inspired the other way around? Can we be inspired by these processes and use that to our advantage for different applications? It's clear that these plasmas are not our usual laboratory plasma. So in most of these astrophysical environments, you have electron-positron pair-dominated plasmas. Relativistic, in some of these cases, the general relativity effects do become important. And on top of that, you can have very strong fields, including fields above the Schwinger critical field, where strong coupling with radiation and copious pair production become quite important and need to be taken into account among many other processes. So we want to understand how the energy partition is shaped by these plasma and strong field processes in these environments. as we've also heard in these different talks, kinetic simulations, in particular particle and cell simulations, have been one of the main tools to study the nonlinear physics associated with these extreme plasma conditions in the last 1 or 2 decades. And in particular, we've seen quite important advances, developments in these codes to include the additional physics beyond just collisionless plasma physics that you need to capture what's going on in these environments. This includes, for example, GR peaks, so including general relativity in these codes, strong field QED processes, both pair production and different radiation emission processes, which allows us to study this nonlinear interplay between the plasma, the strong electromagnetic fields, waves, the energetic particles, and the energetic photons. Okay. And so obviously different processes operate at the most basic kinetic level in these environments, and we want to understand them from a first principles perspective if possible. And so I'll just give some examples also based on what we've heard in these last 2 days of what some of these very fundamental processes may be. Close to these compact objects, for example, we are interested to understand from first principles how QED cascades populate the magnetospheres of these objects with pair plasmas, and how this process, for example, can lead to oscillations in E parallel that could be responsible for coherent emission, for example, in polar caps of pulsars. We've heard also about fast radio bursts, and how understanding these may require understanding the propagation of these very strong electromagnetic waves in these magnetized environments, and potentially how they give rise also to coherent synchrotron maser radiation that could be responsible for fast radio burst emission. We want to understand how the magnetic energy in these systems is efficiently dissipated potentially into energetic particles. These may involve combination of large-scale instabilities in these environments, like in these relativistic jets, operating together with turbulence and magnetic reconnection. We just heard Stas today, for example, discussing this. There's been a lot of work using first principle simulations, try to understand how these different processes affect the ability of these plasmas to accelerate non-thermal particles in an efficient way. And finally, in some of these environments, maybe the ambient magnetic field is not so high, but you are dominated by the kinetic energy in this plasma flow, say, and you want to understand how the plasma itself at the very basic microscopic level manages to amplify the fields by itself, produce shock waves that are then efficient at accelerating particles, both from non-relativistic to highly relativistic environments. So what I wanted to stress here is that a lot of these developments from the simulation side have actually been done in parallel as well by the community trying to understand some of these extreme plasma processes in the lab. In particular, people looking at particle-based accelerators, trying to understand how the next generation high-intensity lasers interacting with plasmas behave. They are trying to add exactly the same physics, for example, these strong field QED processes in their codes. And these developments that are emerging based on these experimental opportunities, I think, share a lot of interesting aspects with what is being done from the plasma astrophysics side. And so I want to tell you more about what exists today, what are some of the studies that are underway to study some of these basic plasma processes under extreme conditions, and what might be possible also in the next couple of years. So I'll go a little bit in the reverse order, start talking about what are some of the experiments that are being done in collisionless, initially unmagnetized plasmas, and then move towards the higher intensity, so relativistic pair plasma, strong field QED, those kind of processes. There's different facilities being used, going from high-energy laser systems, such as the National Irrigation Facility, which you've certainly heard about, when 3 years ago they achieved ignition in inertial confinement fusion. It turns out that they also dedicate, unfortunately, a very small fraction, about 5% or so, of their beam time to the international community. So it's possible to propose experiments that take advantage of all this energy in these lasers to drive, for example, plasma processes in these different conditions that we would like to study. There's also very significant development in high-intensity lasers. A few years ago, we had the Nobel Prize for Jean Moreau and Donna Strickland with the technique of short pulse amplification that allows us now to have very high intensity, very short pulses. And we will see what can some of these drivers do for us as well. At the same time, accelerator facilities that can produce 10 GeV electron beams, for example, to power free electron lasers, are also being used to study plasma-based accelerators, for example. That could be interesting connections to be explored there. And finally, at the highest energies, proton beams, like the ones that are used in CERN, could also bring interesting opportunities, and I'll touch upon that as well. All right, so I decided that there's different parameters that we can use here to guide what the different facilities can do in terms of different plasma and field parameters. I decided to use field intensity here on the vertical scale, so in this case measured in watts per square centimeter, and the total energy of your driver in the x-axis. So this goes from 1 to 1 megajoule, and here we go from 10 to the 10 to 10 to the 30. And I have 2 horizontal lines here. Thank you, Andre, for introducing this earlier today. I think Sam also mentioned this yesterday. So this is the field strength parameter, A naught, okay? If you want, tells you about the normalized momentum of the electrons in the quivering in the laser field, okay? So for typical lasers, the frequency or the wavelength of these lasers that we use is about 1 micron. And so this becomes larger than unity at intensities of around 10 to the 18 watt per square centimeter, okay? So the electrons quivering in the laser field, the electromagnetic field, will become relativistic. So we are in a nonlinear regime. Then we have this line up there, which is the intensity corresponding to the Schwinger critical field, which is 10 to the 29 watt per square centimeter, okay? And we will my goal is to tell you how some of these advances in light sources and accelerator facilities and diagnostics, which are very important associated with this, are allowing us to probe different plasma processes, to test this, use this data to test numerical codes, for example, and develop better models. So in terms of lasers, we have 2 big categories here. Lower intensity, very high energy lasers like the National Ignition Facility, and short, high intensity lasers like, for example, the Eli in Europe, the Zeus facility in Michigan here in the US, the EP also here in Omega in Rochester, and Corel's in Korea. So these lasers now are starting to reach intensities above 10 to the 33 watt per square centimeter. So the A naught, this field strength, can reach about 1,000. So it's very, very large. At the same time, in accelerator facilities like at Facet 2 at SLAC, we use a 1 mile long linear accelerator to produce 10 GeV electrons. And it's now possible to actually focus or compress these electron beams to have very high intensities, actually near equivalent to what some of these higher intensity lasers can do. But now we have a driver that is made of 10 GeV electrons. We also have, for example, I'll talk a little bit about this, the 400 GeV proton beam at SPS, which can carry a lot of energy. And as we will see, could be used to drive copious numbers of relativistic pairs and produce a pair plasma based on this initial driver. An important realization that is driving a lot of these efforts from the laboratory side on the strong field physics is that even though the laboratory intensity of these fields, so in the lab frame, is still very far from Schwinger critical field, the quantum strength parameter chi, which is the ratio between the electric field experienced by, say, an electron in its frame compared to the Schwinger critical field, can actually exceed unity if you now collide one of these very energetic particle beams with a high-power laser. Okay, so the field of the laser is going to be boosted by the Lorentz factor of the beam. So if you have 10 GeV, that's going to be a 20,000 factor. And so under these conditions, in these collisions, the electrons will experience a field strength that is larger than the Schwinger critical field. Similar ideas are done based only on lasers, where, for example, you have two lasers. One is used to drive via plasma-based acceleration, multi-GeV electron beam, and then you could collide that with the other laser. Or as we will see at the end of the talk, we could actually form kind of an electromagnetic trap where we have two colliding, very high-intensity lasers, and the electrons trapped in this field will be accelerated and collide with the lasers to experience these very large field strengths. Okay, so this is what I'll follow. I'll give some examples of works that are being done along these different energies and intensities, starting here on the low intensities, high energies. And so in particular, I'll tell you about some of the work that we've been doing on trying to understand if we can use these very high energy drivers to produce collisionless shock waves in the laboratory and study the energy partition associated with these waves. Naomi yesterday talked about the very high energy limit of this problem. So how are the highest energy particles produced potentially in these shock waves? We cannot do much about that, but we are interested in studying the very early phase of these shock waves. So if we have two counter-streaming, high Mach number, collisionless plasmas interacting with each other, how do they form a shock wave in first place? How do they self-amplify the magnetic field in the plasma to produce a shock wave and then to accelerate particles? And what are the collisionless processes that control how the energy gets partitioned from the kinetic energy of the ions in the beginning, say, to the temperature of the electrons after the shock is formed? And so typically the way this is done is you have two solid targets, can be made of plastic for the argument's sake here. We radiate them with high-power lasers, typically nanosecond duration, intensities on the order of 10 to the 15, 10 to the 16 watt per square centimeter. The field strength is so strong that you're going to ionize very quickly the targets as the laser interacts with it to create a plasma. And this hot plasma plume is going to expand into the vacuum, typically with velocities of a few thousand kilometers per second. Okay? So you can do the same thing on this side, and I'll study what happens if I have two energetic plasmas moving at more than 1,000 kilometers per second colliding with each other. Are they going to produce strong fields? Are they going to produce a shock? What conditions do I need in order to do that? And so just to give you an idea, as I said, so the typical velocity is on the order of 1,000 kilometers per second. Magnetic fields can be very large, and density is very large as well compared with astrophysical plasmas. But in terms of the dimensionless plasma parameters that actually determine the kinetic physics of these plasmas, they are in relevant limits, for example, to understand young supernova remnant regimes. So we have a collisionality that is very low, meaning that the mean free path between ion-ion collisions is about 2 orders of magnitude larger than the system size. And both sonic and alphenic Mach number are very large. So we want to understand what happens in these conditions. So here's an example of results from earlier experiments that were done at the Omega laser facility, a little bit less energy, but the setup is about the same. You collide these two plasma flows. And in these first 2 columns, I show you proton radiography. So we have a source of protons with 3 and 15 MeV that are going to traverse the interaction region. If these plasmas cross each other without producing any strong fields, you would just collect kind of a uniform proton irradiation in your radiochromatic film. If there are strong fields produced, they're going to cause small deflections of the protons, and you use that to image the field structure. And so what you see here is experimental measurements at 2 different times and 2 different energies. where you clearly see the development of these filamentary structures, filamentary fields in the interaction region. On the right, you see synthetic radiographs based on 3D particle and cell simulation. So we take the measured plasma profiles from the experiments, we insert that in 3D particle and cell simulations, we radiograph them the same way that is done in the experiments, and you see very consistent structure in terms of the filamentary patterns that we observe. And so by doing this type of experiments, we're able to show that these plasmas can self-magnetize to via these kinetic instabilities to levels on the order of 1%. So about 1% of the kinetic energy density in these flows gets converted into magnetic fields at the ion skin depth scale in this case. This is associated with instability called current filamentation or rival instability. I think most of you are probably familiar with that, but the ones that are not, let me just very briefly explain the physical principle behind it. This is associated with an isotropy in the velocity distribution. Okay, so if you consider two symmetric counter-streaming plasma flows that are flowing in this direction, and now initially they are current and charge neutral, now we consider a small magnetic field perturbation with wave number perpendicular to the velocity of these flows. What you'll see is that this magnetic field is going to pinch particles coming from the right and from the left differently. And so this is going to induce a small perturbation in the current of the plasma, which is going to reinforce the initial perturbation of the magnetic field, okay? So you have an instability, we'll have magnetic field that surrounds these current filaments growing exponentially with a growth rate that is proportional to the plasma frequency. And this process typically saturates, so the ultimate limit where it will saturate is when the fields are so strong that the gyro radius of these particles becomes compatible to the separation between these filaments. This is also known as the Alfvén limit, okay? And so we expect that this instability can, which is operating at kinetic scales, can transfer 1 to 10% of the kinetic energy of the flows into these magnetic fields, and this is what we see in these experiments. In order to form a shock now, we need to drive this instability for long enough that these fields start impacting the propagation of these flows, deflecting these particles in order to produce a shock wave. And this is why we had to go to NIF. So that we have a large enough system size in terms of plasma scale. So what we have here, which is about 2.5 centimeters between these two foils, corresponds to 1,000 ion inertial lengths, okay? So this is about the largest system sizes that we can do, where we have high Mach number, collisionless plasmas interacting with each other, okay? This is actually a photo of our targets. Then we use a suite of diagnostics to characterize the plasma conditions. In particular, we measure with Thomson scattering the density, the temperature, the velocity of the flows here at the interaction region. We can do this for one flow alone, and when two symmetric flows collide, so we see what the interpenetration of the flows, how it changes the properties of the plasma. We can use that the X-ray self-emission from the plasma. You see here with on flow only. When the two flows collide, you see the very strong brightening of the central region here, associated with a shock that is formed. And we also have electron magnetic spectrometers that we use to measure accelerated electrons in the interaction. So again, you see here, when there is only one plasma flow, not much happens in terms of particle acceleration, but when the two plasmas collide and they form a shock, as you will see, you get very strong non-thermal acceleration. So these are some summary of some of our main measurements. Here on the left, you see the electron density in the midplane where these two flows collide as a function of time. If you just have one of the flows, this is the profile that you have. If you just have now two symmetric flows that just cross each other without anything interesting happening, you would just double this profile. What you see is that the plasma is strongly compressed by 4 times the initial density. This is what we expect from the jump conditions for a strong shock wave. On the right, we see the non-thermal spectrum measured in these experiments for the electrons. So we actually know what the electron temperature in the shocked plasma is. We measure that with Thomson scattering, is 3 keV. And so what we see is that we are producing electrons going all the way to 500 keV, so more than 100 times the thermal energy at the shock. So these are clearly non-thermal. If you look at their maximum energy, it is consistent with the Hillas type criterion that takes into account the fact that the acceleration is limited by the transverse size of your system, which is about 0.5 centimeter here. So we cannot accelerate more than that because the electrons escape due to the finite size of the system. And so this is inspiring us to, based on these data, to try to constrain, for example, models for electron injection in some of these collisionless shocks in the high Mach number limit. More recently, we have also been trying to understand what controls the energy partition in these shocks. As you may know, this is a poorly constrained, it's a very fundamental open problem. So in a collisionless shock, how does the initial kinetic energy of the ions get partitioned behind the shock between electron and ion temperature? Okay? We know that in an aerodynamic shock, there's time for equilibration between the two species. That's not the case in a collisionless system. Okay? At low Mach numbers, this is relatively well constrained and understood from spacecraft measurements. But in high Mach numbers, observations from Balmer-dominated supernova, for example, are not too constraining at the moment. And so what exactly controls this energy partition? And so in these experiments, for example, we can actually see how the electron and the ion temperature vary as the shock is being formed. Okay? This is the electron temperature. You see a very fast rise all the way to 3 keV, and this is the carbon. So most of the energy this is carbon with deuterium or carbon with hydrogen. So most of the energy is in the carbon. You see it increases all the way to 30 keV, and at some point here, basically, your transverse expansion starts to dominate. So basically, your shock plasma starts relaxing. And so based on these measurements, we can infer what the temperature ratio is between the electrons and the ions downstream of the shock. One thing we have to be careful with is that even though the ions are collisionless, so their mean free path is very large, the electrons not so much. And so we need to understand whether the friction, because these electrons are now subject to the friction on these counter-streaming ions, is playing an important role in their heating or not. So we can actually constrain that quite well. You see here the comparison between the theory and the numerical simulations for the plasma flows measured in the experiments of what that friction contribution to the heating is. And it's about 0.7 keV out of 3 keV. So it's not zero, but it is subdominant. Okay? And so based on this, we can infer a collisionless temperature ratio, which is on the order of 0.3 to 0.4. We have more recently done the same experiments now with beryllium, where you can lower the Z and the collisionality and confirm indeed that in the collisionless limit, this is about the temperature ratio, 0.3. And so this has also inspired some of the work to try to understand in these high Mach number shocks what exactly is dictating this temperature ratio. This is work by Arnaud, who is here, where the idea is that this magnetic turbulence that is driven ahead of the shock by this Weibull instability, for example, is going to affect electrons and ions quite differently. So as this plasma flow comes towards the shock, the electrons become magnetized in these magnetic fields. The ions are not. So the electrons are kind of tied to the instability frame, to the frame where the instability is purely magnetic, whereas the ions are able to traverse these turbulence. And so this differential in velocity between the electrons and the ions is going to set up an electric field that is responsible for the energy exchange between the ions and the electrons. We show that this is primarily controlled by this psi parameter, which depends on the ratio of the masses and the ratio of the scattering frequencies in these turbulent magnetic fields. Now, this depends on this is quite general up to here. Now, it depends on what the structure of the magnetic turbulence is. What we show is that this depends primarily on the ratio between the K parallel and K perp of these magnetic fields, which in the case of the ion Weibull instability is about unity. So both of these are on the order of omega pi over c. And in that case, you see that you pretty much maximize this temperature ratio, which is about 3.3, and is consistent with what we are seeing in these experiments. Okay, so now I want to tell you about where can we go as we move to these higher intensity short pulse lasers. I'll tell you first about some of the efforts along some of these similar lines, and then some other research directions. So as these intense lasers shine on these solid targets, they not only ionize these targets, as I was showing you in the previous couple of slides. When the field intensity or the strength parameter is very large, much larger than unity, they will also produce relativistic electrons, a very large number of those that will propagate through this very dense, so solid density plasma. So the idea is if you now shine one of these very intense lasers on a solid target, the laser cannot propagate in the target because the target is overdense, but it produces large amount of relativistic electrons that will propagate through the target. Okay? Now, as you know, the plasma wants to stay charge and current neutral, and so as you drive these megampere current of fast electrons in your dense plasma, the return current, so the background electrons will quickly respond to try to cancel this current, so they will drive a return current. So you have all these relativistic electrons moving forward, and your denser background is moving slowly backwards in order to cancel this current. And so this will drive these counter-streaming electron populations. One, the fast one that is very hot and lower density, and then the background that is cold but dense. Okay? And so this brings interesting aspects that are not fully understood in terms of the development of these instabilities. What happens when these electrons now are relativistically hot, in particular when their transverse momentum is larger than the mean momentum with which these flows are moving? It is expected that you can stabilize the instabilities in this case, at least these perpendicular instabilities. When the flows are very asymmetric, so in this case we have hot and low density versus cold and high density, electrostatic effects can become important as well. We have another complication that in these very dense, like solid density plasmas, resistive effects, at least in the return current, can become important too. And we also would like to study what is the saturation and nonlinear dynamics of these instabilities. Now the challenge is that at solid densities, these instabilities develop on microns or submicron scales, okay? And so we cannot use optical diagnostics at such high density. And so really the way to do that, and took quite a while, but we're very excited about this, is to combine these high-powered optical lasers with an X-ray free electron laser, okay? And so these are experiments we did at LCLS, at SLAC. In this case, we use different type of targets, copper or aluminum wires. We use this high-power laser, short pulse laser, to irradiate this wire to produce these relativistic electrons. And then we use the X-ray free electron laser that now has the penetration wavelength to be able to probe this high-density plasma and the coherence in order to be able to resolve like these submicron scales. And so we can now resolve what happens inside this plasma going all the way to sub-picosecond to nanosecond time scales. We see very different phases. I'll discuss primarily this first phase, where we see the filamentation developing in these targets. And so here's a set of images with different times. The laser is coming here from the left-hand side. These are X-ray images. These vertical bands that you see are the limits of the wire targets. And you see now this filamentary structure developing in time over tens of picoseconds, okay? So you see that they start appearing about, depending on the target, between 2 and 3 picoseconds. So that was the first thing that was puzzling for us. This was slower than what we were expecting. If we were thinking about the instability of the fast electrons, they should be unstable on femtosecond timescales if you consider the cold limit. And so clearly, their temperature is strongly impacting their ability to become unstable. On top of that, what we are seeing here are density modulations, okay, of the total density of the plasma. And so this is telling us that electrostatic effects must be important, and that ion motion must be important, okay? And so it will turn out to be the case in such an asymmetric regime, the instability only develops if the ions can move. Because if the density of the beam is so low that for you to develop significant density modulations in the two populations, the ions need to provide the charge neutralization. So they actually need to move sideways in order to maintain the plasma quasi-neutral. I can tell you more about that and the comparison with the simulations in the theory later on if you are interested in. But I wanted to point to the ability now to actually resolve the nonlinear dynamics of these filaments. There's been quite a lot of discussion about that. So these are very small scale filaments. Can they actually grow to larger scales or not? The idea is that these currents can attract each other through the magnetic force. Misha, who I think is here, has worked this out 20 years ago and derived the model for the evolution of this filament wavelength by these binary attractions between filaments in the nonlinear stage. And you can see that this agrees quite well. It's quite consistent with what we are measuring in the experiments, from which we can actually infer what the strength of the magnetic field is in these filaments. And it's on the order of 10 megagauss, so 1 kilotesla. Okay? So we're producing very strong fields inside this dense plasma. And from the point of view of the plasma physics, what's important here is not if it's Tesla or 1,000 Tesla, is that this corresponds to the Alfvén limit for the fast electrons. So these fast electrons are able to drive strong fields where basically they are strong enough that will confine themselves within these filaments. And so this has important implications, for example, for the transport of relativistic electrons in plasmas. All right. So enough of filamentation and unmagnetized collisionless shocks. I want to tell you about, even though I'm not working on this, some of other exciting work that is going on. Louise is here. She has been driving a lot of the efforts on studying relativistic magnetic reconnection in the lab. So the idea here is that, imagine that this is one of your solid density targets. If we now shine two of these intense lasers on these targets, you are going to produce these plumes of very energetic relativistic electrons. And just outside the target, they will actually be able to carry magnetic field. If you think about magnetic field from misaligned density and temperature gradient, so Biermann battery-like fields, they are going to be toroidal fields that surround these plumes. And as these electrons expand at near the speed of light, they will carry magnetic field with them, okay? It turns out the topology is such that these field lines are going to have opposite direction here in the midplane, and so this should be able to drive magnetic reconnection in these conditions. And so these are K-alpha images, so the idea is that these electrons, as they move towards the target, they are going to excite K-alpha emission. If you just have one laser, you just see this blob coming from the laser plasma radiation. Louise shows in her experiments that if you just do the other laser, you just have the opposite. You have nothing in the middle. When you now combine the two, you see this beautiful brightening here in the center associated with electrons accelerated in the current sheet associated with magnetic reconnection. They also find evidence for non-thermal acceleration of electrons when they measure the spectrum from these experiments. These are different experiments with different laser systems, but I wanted to include this just to also highlight the ability to exquisitely measure the profile of the magnetic fields in these experiments using proton radiography techniques. And so we are now being able to produce conditions where, at least for the electrons, so the ions actually don't play much of a role here. This is too fast for the ions. But the electrons have sigma on the order of unity. So the magnetic energy density is comparable to their rest mass energy density. These, of course, these experiments are very short in time, but I think there's exciting opportunities here to study some of these reconnection physics in this regime. All right. So I'll now move away from lasers and tell you about some ideas that could be explored with 10 GeV electron beams, namely the one at the SLAC FASTA2 experiment. So this experiment is aiming at, the main goal is to study plasma-based acceleration. So they use this 10 GeV electron beam to drive a plasma wave behind it and to accelerate particles in the wake of this electron beam. As you know, there's now a lot of interest in studying synchrotron losses and plasma emission associated in these highly magnetized environments, coherent emission mechanisms. My colleagues at IST, Pablo Bilbao and Luis Silva, for example, have been showing that when you take into account radiation reaction in these strongly magnetized environments, you can produce ring-like distributions in momentum, because the higher momentum particles will radiate faster than the lower momentum ones. And this could drive electron synchrotron maser instability and coherent emission. It turns out that producing that same condition in the lab, the magnetic fields that you would need are currently not available. But there are interesting similar ideas that potentially one could explore. In particular, people in the plasma accelerator community are very familiar with what is known as the Betatron oscillation or radiation. The idea is that as energetic electron beam that is very short propagates in the plasma, it is going to drive a plasma wave. This is basically it's going to expel the electrons from the plasma and leave behind the cavity of ions. So there's going to be a radial electric field that is focusing for the electrons. And so as electrons are displaced from the axis here, they will suffer a restoring force, which will make them oscillate around the axis, and they will radiate due to this motion. And so because the force that they experience is depends on the radial position, they will also, the ones that are further away, they will radiate more than the ones that are closer in, and this will also lead to a ring-like distribution to develop. So if you look at the spectrum here in momentum of these electrons with radiation reaction off, you just have this Gaussian-like distribution, but if you have radiation reaction on, you start seeing this ring-like distribution developing. And so you actually see this also in the spatial distribution here, these ring-like structures forming. And so this could be an interesting platform to study how these ring-like distributions are unstable and what are some of their radiating properties. All right. And I want to tell you about producing pairs, how we can use these high-intensity lasers and high-energy proton beams to try to produce enough relativistic electron positrons that we can actually call it a plasma and start potentially doing some plasma physics with it. On the laser side, there's been quite a significant effort in the last 20 years or so to use these high-intensity lasers to produce, again, lots of relativistic electrons that will then be used to produce pairs. There's two main mechanisms being explored. Just make sure I'm okay with time. Being explored, the first one is called the direct method, where these lasers impinge directly on a high Z target, like gold, for example. They're going to produce these relativistic electrons that are going to drive Bremsstrahlung radiation, which is going to decay into pairs via a Bettle-Eitler process in the strong nuclear field. And so you produce these relativistic electron-positron pairs that can then be measured and studied. An indirect method as an intermediate step, where first the laser interacts with a gas jet to produce a very energetic electron beam via plasma-based acceleration, and then it's this beam that interacts with the target. The concept is similar. You see the examples of electron and positron spectrum produced from the first method and from the second one. So basically here you have lower energies, so 5 to 10 MeV, but very large number of pairs. In the other method, you produce much more energetic pairs, so hundreds of MeV, but lower number. And these different groups have shown that you can actually control the neutrality of these beams, so this ratio, by either changing the thickness of these targets or by using a magnetic collimator and energy selector after the production of the pairs. Very recently, the team of Gianluca Gregory at Oxford used the SPS beam at CERN in the high red mat facility to also produce very dense relativistic pairs from the interaction of these 400 GeV proton beam with a graphite and tantalum target. Okay? The idea is that these 10 to 11 protons, as they interact with a solid density target, they will produce pions. Neutral pions will decay into basically a beam of GeV gamma rays that will then pair produce in the target. And so by doing this, they were able to produce about a few times 10 to the 12 pairs with a density of about 10 to the 11 particles per cubic centimeter. So if you now ask, okay, what do I need in order to be able to produce a plasma? So I need to have relativistic pairs that have a volume that is larger both than the biosphere and also the relativistic skin depth of the plasma. And so this is the condition that is here in the solid blue line. Okay, you see that it doesn't depend only on the number and the density, it depends also on the relativistic factor of these pairs. And so you see that these different laser experiments are slowly approaching this limit, and this new experiment using the proton beam has actually just crossed that limit. And so we are now in conditions where for the first time we are producing relativistic pairs that are dense enough and numerous enough that you can actually call them a relativistic pair plasma. Maybe this is not so exciting for you. It was just starting to be able to call this a plasma, but I think there's interesting opportunities. I'll talk about some of them in the next couple of years, either by exploring some of these similar mechanisms, but at higher laser drives, but also combining these energetic electron beams with lasers to actually go beyond that, potentially to about 10 skin depths in each direction, so 10 skin depth cube, okay? Okay, I have a few minutes. Finally, I want to tell you about these ideas to go into the strong field QED regime by either combining these energetic electron beams with high power lasers or combining very multiple high power laser fields. One of the most exciting experiments in this direction is also being done at SLAC. Phil and David are here, which are leading this effort together with Sebastian Moyden, who is also part of the SIX collaboration. The idea is that we can collide the 10 GeV electron beam with a 10 terawatt laser. So that's in the frame of these electrons, they experience a chi of order unity, so a field comparable to the Schwinger field. And so here are some of the measurements. This is the spectrum of the electrons as they collide. They are timed with a laser. So you initially have 10 GeV, and you are seeing here the spectrum showing a clear transition between the linear and nonlinear Compton regime. So they're able now to measure this experimentally. You see here when the laser is mistimed intentionally, where you don't have this Compton edge or Compton transition. We see also here the experimental measurements showing the transition from n equal 2 to n equal 3. So we are seeing like this nonlinear Compton regime. So we are seeing the redshift associated with the change in the dressed electron mass in the presence of this very strong field. And so we are now able to probe these strong field effects in the interaction of these relativistic electrons and the lasers experimentally. And I'm looking forward to what is going to come in the next few years, also with the possibility of increasing the intensity of these lasers and probing deeper in these nonlinear strength parameter. Finally, one of the ideas that has been driving a lot of the developments in this field on the laser side, which came from a paper from John Kirk and Tony Bell in 2008, is that if you can combine two of these very intense lasers with intensities close to what we can do today, about 10 to the 24 watt per square centimeter, you can form an electromagnetic trap for electrons, where they are accelerated by the laser field and collide with the opposite laser field in order to produce high energy photons from nonlinear Compton scattering, which will then decay into pairs from nonlinear Bright-Wheeler. And Bell and Kirk show that around 10 to the 24 watt per square centimeter is basically when you have a very fast growth in the number of pairs. So we have a QED cascade, and basically your laser energy gets equally partitioned between pairs and high energy photons. Okay? And so what can be shown is that in these conditions, you can actually produce a maximum plasma density, pair plasma density, that is set by the opacity. So at some point, you produce so many pairs that you start screening this laser field, okay? And so this could be an exciting opportunity in the next few years as the laser developments move in this direction, when you can start producing dense enough pair plasmas that you start screening the laser field and hope to study the interplay between collective plasma processes and these radiative processes in this environment. And there's been many PIC simulations, as I said before, now including these QED processes and showing how these cascades develop from first principles in the collisions of these high-power lasers. All right, so I want to finish here. It's clear that this is a fast-developing field, primarily motivated by the observational discoveries, but also I think by very exciting theoretical and computational developments. And I think that these technological advances in light sources and particle beams and diagnostics can also help us push our understanding of these extreme plasma processes, on top of the impressive progress in the last decade in our ability to do kinetic simulations of these plasmas. These advances in high-intensity lasers and particle beams are also starting to enable studies of relativistic pair plasmas under strong fields, which I think are going to be quite exciting, and establishing new connections between basic plasma science and high-energy astrophysics, which I think are important for us to understand some of these exciting astrophysical discoveries. Thank you for your attention.